Yes, thanks. So I'm going to talk about, yes, using h-Cobordisms to detect non-trivial homotopy groups in spaces of Legendrians. And this is joint work with Yasha, and it's something we've been working on a while. In fact, Yasha gave a talk about some of this 3 years ago here in the Symplectic Zoominar. But it's changed quite a lot since then. So I think it'll be, even if you saw that talk, it'll be kind of new. So the plan of the talk is to, let's see. First, I'm going to introduce what is the space of h-Cobordisms and also a slightly more general space called partition space that was introduced by Waldhausen, I think. I was sad to hear he passed away a few weeks ago, so I never got to meet him, but yeah. So I'm going to introduce those spaces in a slightly different way than Waldhausen did. But then I'm going to describe a map from this h-Cobordism space and into the space of Legendrians in some contact manifold C. And this I'm describing as moving a fold, and this will make sense when you see the construction. Then I'm also going to describe a second type of map, that is type 2 maps, which is called moving a conormal, which is also going to be a map from this into Legendrians in some contact manifold. So these maps looks a bit similar. And initially, we had these maps. And then when we found these other ones, we thought this was just an easier description of these maps, and we were sure they would be the same. But it kind of turns out that they're not the same. And this is part of the story. But first, when you have a map like this, you need to be able to detect this non-triviality I claim on homotopy groups. So the next part after defining the maps is to talk about how generating functions can detect that it's actually non-trivial, at least in some cases. This is not going to be general. For example, we think that many of these are formally trivial. Hence, if the Legendrians you produce are loose, you would expect this to just be null homotopic. But if you have a generated function, you're certainly not loose, and then you can get some results. That's for the type 1 maps. For the type 2 maps, we're going to need something slightly more general than generating functions, which is called generating hypersurfaces. And at this point, I don't know if I will get that far, but it's, yeah, if time permits, maybe I will. And in the very end, if I have more time than I thought, then I'm going to describe an argument for why they're not the same. Meaning that they actually define complementary homotopy groups inside spaces of Legendrians in some cases. Many of these last 3 points here all are in some cases, specific cases. And it's very difficult to write out exactly what those cases are and what the conditions are. So I'm going to write this very weak statement. I write it as a theorem, but I don't know. In many cases, both maps are non-trivial in homotopy groups and independently so. That's really weak, but I think you might at least see some examples of this if I get time. Yes. So that's the plan for today. So let's start with these partition spaces and h-Cobordism spaces. So let them be a compact manifold, and it can have boundary and corners and whatever. In fact, it can be a pretty ugly closed set inside a bigger manifold if you want to, but it doesn't really matter too much. Then we define the partition space of M. And so when Waldhausen defined these spaces, he defined them more like the pictures I'm going to draw or show in just a second. But for the purpose of creating the Legendrians and working with these, it's convenient to describe it as functions. And I will explain how it translates. So it's a smooth function. It's a space of smooth functions from this M cross the unit one-dimensional disk, just an interval -1 to 1. Such that 2 conditions are satisfied. First of all, close to the boundary of both the boundary of M and the boundary of D. Of course, there's 2 pieces of the boundary, but anywhere close to any part of this boundary, It is just the projection to D1. And 0 is a regular value. That's the only two conditions. But the way to think of this as some sort of cobordism, or in fact partition, as Waldhausen called them, is to think of the set that is less than 0 as a cobordism from M to F equals 0. Let me show you a picture in a second. Let me just say that the projection itself, that means this function globally defined, is what we consider the base point in this space. But this is the picture. So F maps this M cross the interval down to the interval, and the preimage of 0 is some smooth manifold because it's regular. And what is below 0 is something we consider a cobordism from M inside this M cross interval. So really, partition space is a space of certain cobordisms. They're embedded into this interval, so it's not all cobordisms. I should say, yeah, the reason Waldhausen called them partition is, of course, because it partitions this M cross D1 into two pieces. The piece I call the actual cobordism I care about, and then the other side, which is also some sort of cobordism. And in fact, it's something like the dual cobordism, but yeah, that won't matter today. And so the h-Cobordism space is a subspace of partitions of M, and it's just those partitions where the sublevel set of 0 is an h-Cobordism. So this picture here is not an example of an element in the h-Cobordism, but if this hole here wasn't there, it would be an h-Cobordism. One of the main reasons to single out the h-Cobordism is really it's to get at Legendrians that has a chance of actually being isotopic to the original Legendrian when I construct maps later. You don't really have to, and I will also describe the map generally on partitions, but yeah, it's easier to sometimes just talk about the h-Cobordism subspaces. Okay, so this is going to be pretty important for the rest of the talk, so maybe I should ask if there's any questions. These spaces will show up everywhere throughout. Good. So that's the spaces. Now I want to describe the first type of map. This was the type of map that I said was moving a fold. And so I let lambda be any Legendrian in a contact manifold, and F is any codimension 1 smooth submanifold. And again, this can have boundary and corners. It's really, you can think of it as maybe just a closed subset inside a codimension 1 submanifold. The boundaries can be really nasty if you want to, but again, it doesn't really matter. And yes, that locally in this contact manifold, we can find by this Darboux-Weinstein neighborhood theorem and the fact that all neighborhoods basically looks the same around a Legendrian locally, we can find a tubular neighborhood F cross D1 inside lambda, such that lambda inside C is identified with this standard picture. So what do I mean by this? So F cross D1 is supposed to be represented by F cross this red line here. And this is a picture of the front projection. So the J1 bundle is, of course, Legendrians in that are uniquely determined by their front projection. So drawing something like this that is just F, and by F I mean basically the 0 section. The front projection lives in F cross D1 cross R, and the R factor is the horizontal factor here. So I'm just drawing what the front projection looks like. But that means that this basically depends only on the last coordinate D1. It's really just the front is given by plus minus 2/3 square root of t to the third. And this is the usual way to write the standard fold. These 2/3 is due to, not really important. So when you have this fold, then the point is you can yeah, well, then we just say that the projection down to the base is the fold goes down to f cross 0, and then of course this double covers f cross 0, 1. So that's another way of describing what the projection of the front is down to the base. Okay. So the way to define this map is if I take a partition that, remember, I think of that as one of these functions that is defined exactly on f cross d1, because it's the partition of partition space of f. And the way I map it into Legendrians of this contact manifold is by simply saying that the front of the new Legendrian should be replaced, not c equal to this thing involving just the t, but I now involve this function instead. And this only makes sense inside a neighborhood where, in this neighborhood where this, it looks like this. So we extend by lambda everywhere else outside of this neighborhood. So I should point out that this is sort of a well-defined Legendrian, precisely because 0 is a regular value. Because when 0 is a regular value, it means we can find a neighborhood around the 0 set of f, and this function just looks like the standard projection to the tubular neighborhood. And then it looks exactly like this locally. So this really is a smooth Legendrian varying inside this contact manifold, depending on what function you plug into this. And it's embedded because this function, when you write it like this, you can also determine the length of the reorbits, which is just 2 times this value that z is, the difference in z value. So it's also just the function value. And as the function has 0 was a regular value, and on the side where this has solution, the function is always positive. And so this is positive. But of course, you also have the negative recourse. So that's the picture of the first type of map into Legendrians. Any questions before? I will go to an example, then we can maybe ask for questions there. So if you consider the Whitney unknot inside the jet space of Rn, then this is front projection is just given by this formula. It's almost a standard fold, except that it meets itself at 0, and this function is not t, it's the radial function that you plug in, or something that depends on the radial function. So this is almost set up directly to use this map. The fold is, of course, out at the boundary is n-1. This is the one-dimensional picture. This is the two-dimensional Legendrian. And when you take the image of this map using this fold, the boundary out of S1, we get a map into the Legendrians in Rn, which will all be isotopic to the standard Whitney unknot, but it's a family of them, or it's an entire, it maps into the space of, it maps to the subspace of Legendrians that are isotopic to the Whitney unknot. Its front projection, you can give it an explicit formula here, depending on the function, which is just plugging in this instead of t. So it's very similar to what was on the previous page. But maybe to make sense of this, we extend the function to negative for values less than -1, because this can get less than -1. So this is, there's no solutions outside of that area anyway, so it doesn't really matter. Okay, so a picture of this is that if I take this standard sphere, now S1, and I look at one of these h-Cobordisms that goes from the sphere to this other sphere, in this case still S1, then what you see in the front projection is some sort of deformed Whitney sphere where the fold itself around this Whitney sphere follows this sphere here. So for each h-Cobordism, we get a Whitney sphere of some sort, or something isotopic to it. What's maybe surprising, at least when we looked at this the first time we were surprised that these are actually non-trivial in the space of Legendrians in some ways. But it maybe is not so surprising because there even maybe this biggest surprise when you hear this the first time is that the space of such spheres is not trivial. I don't.
So Thomas, may I ask a question?
Yeah.
So if I understand well, you perturb your lambda, but you keep f fixed. So you have a hypersurface which doesn't move. Is that the correct way to understand it?
Yes, the f is fixed. Of course, you could move that thing around as well.
No. But can you point on the picture where is f and where is the neighborhood where you change your Legendrian?
Yes,
because that's not completely clear to me on the eye.
So yeah, no. So the thing is, so here, if we're in the previous page, is if we're anywhere, and I picked a neighborhood that looked a little bit like a fold. Now here in this example, I am actually using the actual fold when you project down to Rn as the f. That's why we call it f, because it's the fold. So the fold in this one-dimensional picture is just these 2 points at the ends.
Okay, and so these do not change, and you should perturb in a neighborhood of these 2 points.
Yes. So perturbing in the one-dimensional case is not so interesting because perturbing this point is just moving the point in and out somewhere. So moving these 2 points a little bit. You're moving the fold. So the one-dimensional case is rather trivial.
But you're moving a neighborhood. You're moving a neighborhood of the point of f. No, f is fixed, but it has a neighborhood that moves.
No, f is not fixed. So you see, let me maybe go back here. So when you look at this picture here, if I had a fold that projected to just sort of the middle line here, the base point, but the h-Cobordism,
okay,
that would be the original fold. If I now implant this h-Cobordism here, or this function that gives you this thing, then I get a new fold. So the fold is moving in this family.
Yes, sorry, because D1 is -1, 1, not 0, 1. Okay.
Exactly. That's why this choice.
Sorry, I got confused. Yeah. Okay. Sorry.
Yeah. Okay. So this fold is really moving, and you also see this in this picture here that the red seems to be deformed based on this circle here.
Okay. Yes. Okay. Sorry.
No, that's good. Yes. So any other questions? Because this was the first type of maps and the example I was going to give of this type of map. Okay. So the second type of maps are moving a conormal. And what we start with is we consider the contact manifold of the unit cosphere of some smooth manifold. But then we take, again, a general Legendrian inside a contact manifold. But then we assume we have some sort of, I would call it a chart, maybe in some sense, that it's sort of identifying, it's embedding the co-unit sphere of some M cross D1 into our contact manifold of codimension 0. So it's really just charting part of it, identifying a part of it with this conormal of M cross D1. And we want this to be with respect to the Legendrian inside C, such that if we take the Legendrian and intersect with the image of C, then we get exactly the conormal of M cross 0 and the unit conormal. By that I mean the normal to M and then intersected with the sphere. So that's a Legendrian in here. So we want lambda to coincide with that Legendrian, except want one more thing. I want it to be the directed conormal. So I'm assuming that when I have a codimension 1 submanifold, I will want it to be co-oriented so I can pick out a single direction. So I really want that the positive side of M coincides with this lambda in this inside this part. Given that data, I mean, you could also, for example, C could have been all of this, which it will be in an example in a second. And then lambda is just this thing, the conormal of this thing, and then you move it. But yeah. Now we can define a map again, and this is pretty easy. It's actually easier to define than the other one. And as I said in the beginning, we thought it were the same. That was wrong. We define from partitions of M, meaning functions that gives you this cobordism, or gives you this sort of end of a cobordism, is maybe the most important part, where the function is 0. We embed it into Legendrians. We construct the Legendrian in C that is given by, instead of taking the conormal of M cross 0, we simply, which was the base point in some sense in this space of partitions, we replace it by the conormal of the 0 set of F. And then we extend by lambda elsewhere. So let me maybe just go back quickly to this picture again of this thing here. So if it looked like the conormal of just the standard straight line going down here, then we replace that conormal part with the conormal of this red part. So that's another way of creating a family out of h-cobordism. And in fact, for partitions, in both cases, partitions are enough for these maps. So let me take an example, but it's almost trivial in some sense, given how it was defined. If I take Q inside Q cross R, and Q is now a closed manifold, smooth manifold, then I can take its oriented conormal, which is just a Legendrian inside this unit conormal of Q cross R. If you like the language of microlocal sheaves, then you might want to think of this as sheaves that's 0 on below 0, and then it jumps up to have rank 1 below above 0. So then what it generates is roughly this. And also there is some sort of deep connection of all of this to sheaf theory. As I said, we will be using generating functions to detect these. And generating functions gives you sheaves. But sheaves somehow forgets a lot of information. And this is kind of not going there, not going to the sheaf world, because it really forgets quite a lot of information. If you actually did some algebraic K theory with the sheaves, maybe it wouldn't, but that's a different story. But this is staying in this world of generating functions and instead of sheaves. But a lot of this sort of can be thought of as microlocal support for some sheaves and similar things. Okay, now we just move HQ maps into Legendrian simply because it moves. So now instead of taking the conormal of the standard thing, we basically just take the conormal of this moving thing, which, let me go back to the picture again, because I realized that was a nice picture. If it corresponds to saying that we take the Legendrian that's represented by the sheaf, whose support is maybe this yellow thing, rank 1, and then the white part is rank 0. So it jumps, so it gives you the conormal of this red thing. But that's a family of Legendrians because, let's see, where were we here? Because this is an entire space. There's a continuous family of Legendrians inside the space of Legendrians. And as I almost already said, if you take the projection of these Legendrians down to Q cross R, they're actually smoothly embedded. This is not common for Legendrians in this space, which I will get back to. Okay, so that's example of type 2. Now there's a combined example of these two, which is interesting for the last thing, where I want to argue, if I get there, that that they're actually different. So if I consider the jet 1 bundle of Rn, this is a subcontact manifold inside the unit co-normal of Rn cross R. And any Legendrian inside this jet bundle is mapped to a Legendrian whose projection to Rn cross R is in fact the front projection of this lambda. So this is a good way to understand this map into. So you're basically just the map from, if you have a Legendrian in the jet bundle, look at its front projection, put that in Rn cross R, and then take its directed conormal. Then you see what Legendrian actually was defining in here. So that makes me able to take this Whitney sphere that we were looking at. So if I take this modified Whitney sphere where the fold, the red part is moving around, then because it's only the red part that's moving around, I can keep it standard in this brown area on the top of the sphere itself. There it never changes, or at least I can make sure that the support of the functions are such that it never changes. It's not a difference. And then I can just assume that this brown part always agrees with the standard Whitney sphere. And now I'm drawing the projection. This is, I shouldn't call it the front projection anymore, because now it's the projection from the unit cosphere down to our n cross r that I'm drawing. But now it is an embedded manifold here, so I can identify a small tubular neighborhood of this brown thing cross dn. And then I can define a combined map that applies both type 1 and type 2. I write it suggestively as a connect sum because somewhere in between it's constant. And then, yeah. But it's just saying that if I take an h-cobordism in Sn-1, it's moving the fold. But at the same time, I also take an h-cobordism in Dn, this brown disk, and then I move this top accordingly and take the conormal of that up here in Jet1. Not in Jet1, in here, in the unit conormal of our n cross r. You really need to go into this unit cosphere of our n cross r, because when you put in this h-cobordism here on top of the brown thing, it can get vertical from the point of view of the cotangent bundle, which means it doesn't really descend to a well-defined Lagrangian down in the jet bundle, or down in the cotangent bundle of Rn. So vertical things is not really allowed. And if you only look at the h-cobordism that are never vertical, then that space is contractible. That's like a section, and then you can just, yeah, contract down. So you don't get anything interested. It really has to be inside here. Okay, so, and what I claim, and maybe I'll have a little bit of time to talk about how this is proved, but the main claim, and maybe that's the most important, is that this is actually, in some cases, maybe in this case, it's injective on rational homotopy groups. And these things are rationally non-trivial for large n. I will get back to this maybe later. Okay. So how to detect them? Well, as I said, this first type of family we want to detect using generating functions. So if I have a generating, so let me maybe start by defining a generating function as, it's sometimes not something everybody sees, but let me just, yeah. So a generating function G, in this talk at least, it could, there are more general versions, is a function, smooth function from G cross Rk into R, such that the set where the differential of G restricted to the fiber directions, this is the tangent space of Rk, that's Rk itself, is 0. That means that you should think of this as a family of functions, but still calling it a generating functions. I don't like to call them generating families because I think of families of these things, so it gets a little annoying. So you have a family of functions parameterized by Q, and these are the fiber-wise critical points, and that's this singular set, and you're assuming this is a transverse equation, so that it's a smooth manifold. And then this gives you an immersed Lagrangian, and I only want to describe the front projection because you can use that to recover the actual Lagrangian, so that's enough. X comma V is just mapped to X comma G X V on this subspace, which has dimension, the same dimension as Q, so it's isotropic and co-isotropic. So yeah. Yes. So these things are called quadratic at infinity if they equal some fixed non-degenerate quadratic form at infinity on Rk, defined on Rk. They're called linear at infinity if they equal minus v1. I don't know why I put a minus here. That's weird. At infinity, that v1 is the first coordinate. And the only reason to impose conditions like this, and these are the two nicest and also very important conditions, is that you want to sort of be able to do parameterized Morse theory. So as I said, you should think of this as a Q-parameterized function, and you want to do parameterized Morse theory. And if you don't have some control at infinity, Morse theory behaves badly when you go around in the family. So, yeah. But when you say parameterized Morse theory, you basically also should be saying surf theory. And this is also part of what these h-cobordism spaces are about. Okay. So an example of this is that this Whitney sphere that I wrote the front for before has a generating function defined exactly like this. It's also k is 1. So there's only one. These k coordinates are often called auxiliary coordinates, and there's only one auxiliary coordinate. It's called v here. And it's cubic like this. So linear at infinity is a little bit of a stretch, but you should bump off and make it linear if you want it actually linear, or you should just say it's close enough. But in any case, this generates this standard Whitney sphere. But the point of this is that we can actually lift the construction of type 1 maps to actually construct a generating function for the Legendrian that we're defining, at least if it's in a good position. So let's make some assumptions. So assume we have a generating function with one auxiliary coordinate that's either quadratic or linear at infinity, and it generates some lambda inside the jet 1 bundle. Then assume we're also given a fold, and this is actually a fold over Q. I'm not picking some other rotation and looking at it from another side to make it look like a standard fold. I want it to actually look, it is a fold over Q, which was also the case in the example. And I want it to be such that if I project this fold down to Q, then in a normal neighborhood of this fold, it has the generating function looks completely standard. It is the generating function of the standard fold. This x comma t is still in the base. It's in f cross d1. V is the auxiliary coordinate. And this is the t you plug in to get the standard fold in this direction d1. So assuming all of this, which is maybe strong assumptions, but it's not so bad. Often you can take some submanifold inside your Legendrian and isotope the Legendrian around so it becomes a bit like a fold, and then it looks like this, and you can modify the generating family. So you have a lot of freedom to move things around to get to this position. But yeah, if you're in this position, at least you can define a new generating function depending on f, when f is an h-cobordism. In fact, that works for partitions as well. So I could just have written partition space here. So now we get a generating function where we plug in this f instead of t, and it generates exactly. Oh yeah, we have to bump off. So this f is not really nicely behaved. This v function, this thing changes away from the neighborhood. So you have to be a little careful with bumping off and shrinking and stuff like that. But it works. But if you bump off correctly, then you get a lift of the original thing to Legendrians in this jet 1 bundle. But now I put a G because now this is to signify Legendrians with a generating function. So this entire map lifts to a family of generating functions, generating this family of Legendrian. Yes. Okay, so before I can really say something more concrete about how this detects them, I have to talk about stabilizations. If you've worked with generating functions, you know you have to stabilize them when you do a Legendrian isotopy. So there you have to stabilize generating functions. But that part is maybe well known to many, but I also need to say a little bit about stabilizing h-Cobordisms and partitions, which is very similar. And so I focus on that. So let me try and describe what a positive stabilization from a partition on M to a partition on M cross an extra coordinate is. It's because I had this sort of local picture, or I had things were sort of inside this compact rectangle. I need to be a little careful with how I bump off and how I do things. So what you can do is you can start by shrinking the direction of the interval to make it just much narrower in the middle, close to the base point, a C0 close to the base point, but not really close in partition space to the base point. And then you add a new coordinate v squared. In the new coordinate, you add this v squared and bumping off appropriately. I had a little bit of discussion put in of how you need to bump off, but maybe it's not so interesting. You have to be a little careful doing it the right order. You want to need two bump functions and stuff, and yeah. But the main point is that if you look at the stabilized partition you get, then the sublevel set of 0 is unchanged, meaning that sigma plus of F's sublevel set is the same homotopy type. And the way maybe to think about this positive stabilization is that if you look at this cobordism that's on the here, this thing that's shown here, if you sort of think of it, want to put on an extra chord and you think of it as a three-dimensional thing, then you just make it slightly fatter, meaning that this hole still goes through it and you still have something that only looks like a one handle attached to M over here. In fact, if you did this stabilization to an annuli, you get a solid torus. So if there was like a component out here that just looked like an annuli, it would turn into a solid torus. Okay. Now there's also one way of seeing that this has the same homotopy type, that you don't change the homotopy type, is by looking at the Morse theory. If F were a Morse function, you can build a CW structure per one cell per critical point. Then if you look at this plus sigma plus of F, it has the same critical points and the same Morse indices, and the stable manifolds go inside this inside the piece where the new coordinate is actually 0. So you build the exact same CW complex out of this thing, so you're getting the same homotopy type. The reason I'm saying this is because that makes it maybe a little easier to visualize what the negative stabilizations are. They are very much the same, except you stabilize by minus v squared instead of v squared. But it really changes the homotopy type of F less than 0. In fact, what you're getting is a suspension, a reduced suspension of this sublevel set. And another way to think of it is that it's, in fact, if you look at the part that's bigger than 0, you're positively stabilizing that. So if you had like a free-floating annuli that in a positive stabilization turns into a torus, that means that if you're doing a negative stabilization and you had a hole that looked like an annuli, the hole turns into a torus hole, a solid torus hole. So it's sort of just the dual thing gets the positive stabilization. Okay, but in any case, we define a map from partition of M into twice stabilized partitions by adding both, doing both. This is also standard for generating functions. If you want to stabilize them, you add a quadratic form with both a positive and negative term, and then you do that many times. You kind of need to do that to be able to work with them. And then you define the stable partition space as the co-limit of these stabilizations. And the stable h-Cobordism space is the relevant subspace of the h-Cobordisms. I should point out that both stabilizations preserve the notion of h-Cobordism because of this analysis of the homotopy type. So you have the stable h-Cobordism space is this limit of the h-Cobordism spaces. Okay. The reason why I'm also being a little careful with this is so that you may appreciate these theorems that I'm going to cite now. But first of all, let me say there are many non-trivial homotopy groups of H infinity of M. And I will say a little bit more about this when I show a few theorems that we need to actually see some non-trivial homotopy groups. So Igusa has a theorem saying that when you stabilize, the stabilization map, either of them, is actually highly connected if the dimension of M is high, roughly the half the dimension minus 3, 4. And that's very helpful. That means if the dimension is very high, then we know that in some range, the unstable h-cobordism homotopy groups agree with the stable h-cobordism homotopy groups. So that's one tool that's very important. Then there is some other thing you can do with these h-cobordisms. You can take an h-cobordism on N. If you have N is a codimension 0 submanifold. And again, the boundary of N could be pretty bad inside M. Doesn't really matter, but Hn, you get a map from Hn to Hm by saying that the function you had on N cross D1 looked like the projection close to the boundary, also the boundary of N, which means you can extend the function over all of M cross D1 by extending it by this projection. And this you might want to think of as extension by 0 because you're extending by the thing that defines the base part. So these are, so these are very natural maps. And if they also commute with the stabilization maps, which is not too difficult to work out. So I'm just going to leave it at last. But then Waldhausen essentially proved that if this map I is K-connected, then this map of stable h-cobordism spaces will be K-2 connected. This follows from several of Waldhausen's work, but the idea, the way I think of this is that the stable h-cobordism space can be computed using Waldhausen's algebraic K-theory of spaces. But that's really algebraic K-theory of the ring spectrum, which is the suspension spectrum of a base loop space, which, really you should, in symplectic stuff, it shows up a lot, but it's never the spectrum version, just the chain complex version, chains on the base loop space. So somehow the algebraic K-theory are not chains, but something like the chains on the base loop space computes these spaces. And then you can prove that algebraic K-theory has this property, that if you have a map of ring spectra that is K-1 connected, then in fact the induced map on algebraic K-theory is K-2 connected. So it comes from things that is relevant for symplectic stuff, but is sort of a big machinery that I'm not going to get into more now. Okay, so, but the point is, what we want to just use these simple statements to say something. But to do that, I want to just generalize a little bit these maps. So if I take any smooth map from N, some smooth manifold N to a smooth manifold M, then I can just cross with D2K on M for large enough K and lift it to an embedding. Once I have an embedding, and now I just wrote get an induced map, maybe I should have written a little more. So the way you think of this is that N has now a tubular neighborhood inside this embedding. And you can extend the function by just doing one of these positive stabilization by adding quadratic terms in that new direction, and then bumping off and then extend by 0. So it's some sort of combination of stabilizing and extending by 0. So there are these natural maps. And you get maps from just this unstable h-cobordism into the stable H infinity M. You also get from H infinity N into H infinity M because these commute with stabilization. But this is the map I'm interested in for the rest of this talk. And maybe the most important thing to take away is that these two theorems proves that if N is highly dimensional and the map from N to M is highly connected, then this map is highly connected. So that's a way to detect something. How to detect that will show up in the next slide or two. Okay, so if we have one of these generating functions, there is this standard construction, well-known construction called the difference function. it adds the same number of auxiliary variables, and then you just take minus the two functions, but for fixed x. So it's like the fiber-wise, take the same function and it's negative and add in a new direction. But then you also have to bump off if you really want to make it quadratic at infinity, but that's way to do this. It's critical points are one-to-one with Reeb orbits. This is, yeah, well known, and now I think I'm getting to a point where I shouldn't explain too much. And this is classically used to define generating function homology by taking the Morse homology of this double function, but for some epsilon level. And by this I mean g epsilon means the part above epsilon, the part with value above epsilon, for some small epsilon. And what this is, it's a Morse theory that has a generator for each Reeb orbit and then differentials. The point is that there's much more structure in this space. Oh yeah, already more structure. This has recently been exploited and used a bit by Tanaka and Trainer. They've defined a spectrum out of this generating functions thing because these things are spaces, and under stabilization they behave by these suspensions. So you can get spectra out of this, and then you can get some results out of the fact that they're actually spectra instead of just Morse homology theory. So they exploited that in a recent paper. But what I also want to point out is that you can get even more out of these things because they're not just spaces. They're actually cobordisms. They're a cobordism from, and I want to say from this very large value to this very small positive value. And it's a cobordism that's standard at infinity. So with some sort of repackaging, it looks like an element in partition space. In fact, it's already given as a function and not a cobordism. It's a function. So, oh yeah, I should also say this MK for epsilon very large, for the level set for very large numbers, doesn't actually depend on the generating function. Within the fixed family, if you're saying you have a fixed quadratic form at infinity, then it's fixed at infinity, hence this is fixed, this MK. But it does depend on K, and I'll get back to that. So what you get is that it's almost, and I'm lying just a little bit, possible to define a map from Legendrians with generating functions into partition space of MK. I should put a K in this notation, a sub K or something, because I'm having K auxiliary variables, but yeah. But again, generating functions, they change when you tie k-isotopies and you want to get something that's an isotopy invariant and actually detect families up to isotopy, then you need to stabilize. And so what you really get when stabilizing is that, oh yeah, I should say, stabilizing the generating function gives you exactly the stabilization on the target as well, on this partition space. So what you end up getting is a map that I'm going to call D1, mostly for detecting type 1. From this, from the space of Legendrians with one of these stable generating functions into the stable partition space of Q. And here I'm using a little bit of this MK that shows up as this level set. Basically, when you go to infinity, it converges to having the homotopy type of Q. There is a map from Q and it's highly connected, so it sort of becomes a Q at the end. Maybe I should say that for the linear at infinity, it's actually Q across a Euclidean space. For the quadratic at infinity, it's Q across a large sphere across a Euclidean space. And this large sphere in connectivity becomes contractible when the dimension goes to infinity. So basically, it's Q in the limit. Okay. Now, the last part to be able to detect type 1 is to know that this space of stable generating functions to Legendrian is a self-vibration. And I think, yeah, so I was gonna look up who to attribute this to, because I think last time I gave a talk, I said this wrongly and was corrected. But now I forgot to look it up. I don't know if anyone knows who to attribute this result to as a self-vibration, because it takes quite a bit of work. But yeah. But in any case, it is a self-vibration. And
I
what
think in the Lagrangian case, it's due to Terre.
yes,
In the Lagrangian case, and I think using, I don't know if it was in Chekhov or, no, I think he did also the Lagrangian case using Chekhov's,
okay, that's what
some
I,
of Chekhov's result. So
yes,
there may
yes,
be somewhere a contribution by Chekhov, I would say. But
yes, yes.
I
I
think
think,
the result itself is due to Terre. I think.
okay, okay, maybe that's what I was, yeah, okay. So Terre and Chekhanov. Good, thanks, thank you. So how we detect and how we prove that there's some non-triviality in this map is divided into two steps. First, we prove that when you take your sort of moving the fold, put it into Legendrians, give them this generating function, and then you take this, we call the detection map to partition of Q, then this map is essentially this map induced by I that I said was connected, highly connected, and or sort of were an isomorphism in stable range, depending on dimension and connectivity of this map F into Q. I say essentially because it doesn't actually land in the h-Cobordism part. It's sort of a different cobordism, so you have to do a little bit of work, but it's essentially, and it's almost as injective as that thing, so I don't want to get into that. The other component is that this should have been D1, that if I compose this D1 with the map from the fiber of this map, then it's null homotopic. That means that all those homotopy groups that we find here using this map and this sort of stable splitting back that lives in this space must go injectively into this space because they can't come from the fiber. And this is kind of not too difficult to prove. It just follows a little from the geometry. So, but I certainly don't have time now to say anything about that. But this is the main method of detection, that this composition fits into this greater theory of cobordisms and some transfer maps and also a product, but that's another story. So that's the result for type 1. And it implies that it's highly non-trivial and stable range, this map that we defined, in this case of having a generating function. Then there's the type 2. There we need a thing that I hadn't heard of until a few years ago, but it's in Gromov and Eliasberg's paper on generating functions, but I think I either read it and forgot it or skipped that part when I was reading it because I hadn't heard about this so much before. But a generating hypersurface is a slight generalization, or maybe I should say it's the version of generating function that lives over these unit sphere spaces. So what is it? It's I'm going to define it as a function. It's actually a hypersurface, but I like functions better than surfaces. So I'm going to define it as a function, but I'm right away going to define a surface as the zero set, just as we did for h-Cobordisms. That's sort of the zero set is kind of the important part. And it's transversely cut out, so it's just zero is regular. And if you intersect the surface with the parts for this function that you have defined, which is zero on the first surface, but it has if you think of it in terms dually, it has a gradient pointing orthogonally out of the surface. And that thing, when that is orthogonal to the R2K direction, meaning the auxiliary coordinates. But this is not now, this new R, this R that's put in here, is not thought of as an auxiliary direction. In fact, you can put any manifold here instead of Q cross R. And this generates an immersed Lagrangian a lot in the same way as the Lagrangian case, the Jet1 case and generating functions. Don't have time to get into that. But an example, just to get a feel for how this works, is that if you have a generating function on some space, I don't know why I put 2 here and 2 here, it doesn't really matter. Then if I define another new function that sends x sv to just s minus g of this generating function, then this is one of those functions up here. Maybe I should have given it another name than g. That is a generating hypersurface. Qi means quadratic at infinity. I'll get to that in a second. And it generates this same G under this inclusion of the jet bundle into this co-unit sphere. Unit co-sphere. And yes, quadratic at infinity is the same as for the generating function. It's just that it looks like what you would get if you took the quadratic form as a generating function and plug it in to this example. And the same with the linear. Oh, that's where the minus came from. Cut and paste. Yeah. So that's a generating hypersurface, and it's it generalizes, and you have a theorem similar to this vibration theorem for generating hypersurface if you stabilize them, and you can stabilize them in the same way. And yeah, a lot of things works the same way. So an example is that if I take this, any hypersurface in Q cross R is really a generating hypersurface with 0 auxiliary variables. And what it generates is just its directed conormal. Oh, yeah, I should, yeah. So this means that when we actually constructed this map psi out of just taking conormals of actual hypersurfaces, we automatically have a generating hypersurface because it is a conormal of a hypersurface. And you can stabilize them. There's a much easier map, this I call detection 2, which map this Legendrian to hypersurfaces because they are just hypersurfaces. They're already defined like it. You just forget that it had this transversality condition and you forget everything else. And as I said, again, you have a vibration of the Legendrians with generating hypersurfaces over the Legendrians. And again, we divide it into 2 steps, prove that this phi composed with this detection is just the stabilization map that sends HQ into H infinity Q. And yeah, this is not completely finished. This is one of the parts that is a little open, but we are pretty sure that the homotopy fiber of this map is the same as the homotopy fiber of the other map. That in fact, what you're doing when you're taking Legendrians in this bigger space is that you're extending the base, but you're also extending the fibers because you're allowing a more general type of structure, but it's not completely clear. If it is the same fiber, it would mean that it's rationally null trivial in this case that we're dealing with here. Because the things that generates the 0 section are this space called M infinity and it's rationally trivial. Yes. So that means this is rationally injective and rationally it maps down to this space non-trivially, injectively. Okay, so that was the 2 types and how to detect them. Then there is a little bit on why they're different. And then I want to look at this example again of J1 in Rn and the conormal of Rn cross R, which happens to be as a contact manifold contactomorphic to the J1 bundle of Sn, which is some sort of weird rotation or quadratic dual or something, I don't know. But what's important here is that if I take the J1 of Rn into this unit cosphere and then back into J1 Sn, this is contractible. So this is isotopic to whatever inclusion you want. In particular, it's isotopic to the standard inclusion of including Rn into S1 and then just take J1 of that. It is in fact not equal to that. It is that and then rotated like 90 degrees, I think, which is because of this duality that's implicit in this map. But that doesn't matter. It's isotopic to it. So if we take our Whitney sphere that moved around here in this jet bundle of Rn and map it in here and then continue in here, then our detection method says that they're non-trivial. So that means we know that they're non-trivial inside this contact manifold, which means that we know that this map, the combined map that I was discussing before, actually is non-trivial in the first factor into this space. And by first factor, I mean homotopy groups of first factor. Yeah. And then you can check that our detection of the type 2 thing, which was this thing, the other factor, is actually 0 on this part, which means that Yeah, I'm not going to say why now. I have running out of time, but it implies that these two are actually complementary. So yeah, they're not the same, and they give two different copies of h-Cobordism spaces inside Legendrians. And that's really it, and that's the end of the talk.
Thank you. Any questions?
So you said that you lose something when you go from functions to sheaves, which seems natural, but can you somehow quantify or specify what is lost?
To some extent. So if one actually did sheaves in a slightly different way, where one was using also algebraic K-theory of the associated sheaves and some finiteness, one should be able to detect a lot of these things that are going on here as well.
Mhm.
But what can I say? So there are also the sheaves in spectra. They also exist.
Yes.
And these microlocal sheaves, or these microlocal sheaf theory in spectra, if you do those with algebraic K-theory, you should be able to detect these same classes, because the algebraic of the category of spectra are these h-Cobordisms. So you should be able to do sheaves of spectra in a very advanced way. But maybe also remember the generators and remember that this was Morse theory. So you have like a Whitehead spacer or something that you're taking values in some sense. I'm not really sure how to do that. But some algebraic theory of sheaves of spectra should be able to detect these classes as well.
Okay. Okay, thanks.
So when you do this fold moving, you assume that the singularities are exhausted by folds, right?
What singularities?
Of the front projection? Or am I missing something?
The front projection. So in the first description, let's see here. Here I'm just looking locally at the front. I'm not doing anything away from it. So the front is sort of isolated, right? But here, when you're working with something that's actually projected down, you kind of want the front to maybe be embedded down in the base, if that's what you mean. I mean, the front is just it's the same singularity cross a manifold, the same, just the standard fold cross a manifold. So it's very stable.
Right. Okay. So you kind of by design you're not worried about any singularities except for folds.
Yeah, exactly. It's only folds that are created here. There's no other singularities at all. And that comes because this equation that is this equation here, if you solve it, you will see that it will be smooth when 0 is a regular value for this function f.
So the H principle is not needed here by design.
No, nothing. This is sort of
And what exactly breaks if you start with not an h-cobordism, but by, I don't know, with some arbitrary partition, or maybe in the middle of something, the cobordism, which is not an h-cobordism, but for example, s-cobordism?
Nothing really breaks, to be honest. It's a little inconvenient to do it, because if you take your Legendrian and implant one of these partition that looks like this, then the front gets bigger. And a lot of the things you can do in that homotopy class is really like, just if you fix this one front and then take an h-cobordism from that one, not front, that's fold. Just fix this one model for the fold and then move that fold a little bit. You can get a lot of those classes anyway. So that's one reason. Another reason is that I think these partition spaces have some sort of stable range as well, but I'm not exactly sure what they are. So really for this detection and the stable range and all of that, I prefer using the h-cobordism basis. But
Yeah,
nothing
okay.
really,
I see.
yeah.
So basically, the expectation is that if you really wanted, you could have pushed it to more general setup, but it will not bring any new like classes or whatever.
I mean, potentially it could bring some new classes because there is some information in this homotopy type of how the fold moves around, maybe a little bit. I mean, this fold here has like a one-handle attachment onto the M. This is like some deformation of a one-handle attachment onto M. Now that handle attachment, the family of that handle attachment can also give some homotopy type, but I would call it more classical homotopy stuff because there's also been people creating non-trivial homotopy groups in spaces of Legendrians by taking generating functions on non-trivial bundles. And this is starting to look a little bit like that because you have some sort of thing that can be detected by non-trivial homotopy type of the thing you're moving around. And so it looks a little more like these bundle things, I think, but I'm not exactly sure if they're the same. So in that, for that reason, they also, yeah. It complicates the story unnecessarily, I think maybe is the main reason.
Yeah, makes sense. Thanks.
So we have a question here from Uppsala, close to your office, but not exactly there. What is the expectation for the nearby Legendrian conjecture, say for jet 1 of lambda? So what should we think of the space of Legendrians in general? It should be a very big thing then, probably. But...
I mean, the space of Legendrians of the zero section, isotopic to the zero section.
Yes.
Yes, this can create, that maybe I should have mentioned that as one of the main theorems. In stable range, meaning something like the manifold is dimension divided by 3, we can construct homotopy classes of this space of Legendrians, isotopic to the zero section.
But do we have a kind of a guess for what the full answer should be? It should be some kind of... There should be some nice package of this. Sorry?
Oh, type 1 only. So here only type 1 works because if you don't have this... or maybe you could do something with type 2, I don't know, but I wouldn't dare to conjecture anything. Maybe, I mean, I don't personally believe the nearby Lagrangian conjecture, but if I were to believe it, I might believe that Legendrians were in fact these directly in stable range had homotopy groups of these h-Cobordisms.
Of the Legendrian itself.
Of the zero section, yes. Of the now we're just talking the zero section. There's a lot of other things going around when you're not the zero section.
Yes, it's sure. Okay.
I mean, the generating function homology of the zero section is trivial, which means that this cobordism you get out in this map at the end of type 1, where is it? Here. That I said generally lands in partition space. The reason why it's a partition and not an h-cobordism is because this cobordism has homotopy type, which is the generators of the generating function homology. But if the generating function homology is trivial, as it is for a Lagrangian, because it has no reap chords, then this is actually an h-cobordism. It lands in the path like that. And then I would suspect that this map from H of Q into again to h-cobordism of Q is an equivalence and might actually give the difference. I would maybe conjecture that it could give the difference between Legendrians and Lagrangians.
Okay.
In stable range.
This is Georgios, by the way, not Alex, but anyway, thank you.
Yeah.
Okay, if I may, I have another question. Philip here. So in dimension 2, you don't only have the standard cubic model for the cusp, but you also have the swallowtails, right? How do you deal with swallowtails in dimension 2?
But I mean, in this case, we don't have any swallowtails. We just have, I call them folds because they're Lagrangian, right? I mean, is this what you call the cusp now, or?
Yeah. The end of the fold is the cusp.
Yeah. So we only have folds when you do this construction. I don't know, maybe you can take, if there's another stable singularity that you cross some manifold, maybe you can move that type of singularity in some ways as well. That's this, but how that interacts and what it would do, I have no idea.
Okay, thank you.
Okay, so thanks Thomas again.